All right, so last time someone asked for like a practical application, some pretty intense physics. Well, get ready because we're diving deep into Majorana topoconductors.
Oh, wow.
So we're talking about particles that are their own antiparticles.
It's pretty wild stuff.
It's mind-bending.
It really is, and it's even more incredible because these aren't just theoretical. You know, they're not just in equations. Microsoft claims to have built a chip.
A chip.
Yeah. They're calling it Majorana 1.
Okay. I am intrigued.
Uh-huh.
But before we get to Microsoft's creation,
Okay.
let's back up a little bit.
Sure.
What is a Majorana fermion?
Right.
It sounds like it's from Star Trek.
It does, doesn't it?
Yeah.
So Majorana-Fermion basically is a particle that is its own antiparticle.
Right.
It's like matter and antimatter at the same time.
Wow.
It's a concept that even physicists struggled with for a long time.
Right. So how do we even begin to think about something being its own opposite?
Yeah. So it might seem paradoxical.
Yeah.
But think about it this way. You go to the grocery store.
Okay.
You have a budget.
Yep.
And you have your list of items. You're trying to optimize to get the most you can within your budget.
Sure.
And each item on that list is a binary choice.
Okay.
You buy it or you don't.
So I'm creating like a pattern of choices based on constraints.
That pattern, believe it or not, forms a kind of topology.
A topology.
And now, believe it or not, this relates to Majorana fermions.
Okay, hold on, how?
They emerge as these quasi-particles from the collective behavior of other particles. They're also governed by constraints and interactions. So they exist in a superposition of exist and don't exist. Just like your grocery items. It's a binary state.
Whoa, so the same concept that goes into like optimizing my grocery list is at play in the quantum realm.
The universe loves to surprise us with connections.
Wow.
And just like different combinations of groceries create different shopping lists.
Yeah.
The way these Majorana particles interact creates different types.
Oh, wait.
And the patterns of these interactions define a topology. It's not just that they exist. It's how they exist and interact that makes them so fascinating.
Okay, so we've got these like bizarre particles emerging from a system governed by rules, forming these topological patterns.
Exactly.
And Microsoft built a chip based on this.
They did. They called it Majorana 1.
So how does that work?
The chip uses a special material called a topoconductor.
Oh, okay.
It's a topological superconductor.
Topological superconductor.
Okay, essentially it has two properties.
Okay.
Strong spin-orbit coupling and superconductivity.
All right, so what's spin-orbit coupling?
So imagine an electron spinning like a top. Spin-orbit coupling is a relativistic effect where the spinning electron interacts with its own motion.
Okay.
It's like a dancer spinning and moving across the floor at the same time.
I see.
The spin affects the movement and vice versa.
Yeah.
This interaction is key to creating the environment where these Majorana particles can emerge.
So it's like setting the stage for these particles to come out.
Exactly.
Okay, and what about superconductivity?
Superconductivity allows a material to conduct electricity with zero resistance.
Wow.
It's a mind-boggling quantum phenomenon where electrons pair up, forming what are called Cooper pairs.
So they're like doing synchronized swimming?
Pretty much.
Moving together with no resistance. That's wild.
It really is.
Wow.
And when you combine that with the spin-orbit coupling, you get the perfect recipe for Majorana particles to pop up.
Okay, so we have our topoconductor stage set. Our Majorana quasi-particles are ready for their debut.
Exactly.
But how does all this tie into quantum computing?
That's where the real power of Majorana particles lies.
Good.
And it all comes down to something called topological protection.
Topological protection.
Yeah.
Topological protection. It sounds like a superpower. What does that mean for quantum computing?
So one of the biggest challenges in quantum computing is that the building blocks, called qubits, are super fragile. Like any disturbance can cause them to lose information.
Oh, wow.
It's like trying to balance a stack of coins on edge.
Okay.
You know, one wrong move and everything topples over.
Yeah. That doesn't sound like the most reliable computer.
And that's where topological protection comes in.
Okay, so how do Majorana particles help with that?
Because the information isn't stored in a single fragile qubit, but it's encoded in the topology of the system. The way these particles are braided together, it's incredibly robust.
So instead of those coins, it's like carving a message into a rock.
Exactly.
Yeah.
Even if it gets weathered and chipped, Right.
The message is still there.
Yeah, because it's embedded in the structure.
That's a great analogy.
Thanks.
And that's why Majorana particles are so promising for quantum computers.
Okay.
They're like self-correcting qubits.
So
they can stand noise and disturbances.
Stand up to real-world conditions.
Exactly.
That's amazing. So if we can build these fault-tolerant quantum computers,
right,
what could we actually solve?
The possibilities are immense.
Like what?
Imagine tackling like the most complex challenges in chemistry and materials science.
Okay.
We could design new drugs.
Wow.
Discover new materials.
Yeah.
With properties we can only dream of.
Yeah.
Even break down pollutants like microplastics.
Really?
Yeah.
Wow, so we could solve problems on such a vast scale.
Yeah.
From developing medicine to cleaning up the environment.
Right.
All thanks to these tiny particles.
It really shows how everything is interconnected.
Yeah.
How something so abstract like Majorana fermions can have real-world impact. Wow. And that's just the beginning.
And that's just the beginning. Quantum computers could revolutionize artificial intelligence.
Oh, wow.
Enabling machines to learn at speeds we can barely comprehend.
That sounds exhilarating and terrifying.
It is.
Yeah. Are there any downsides we should consider?
Of course. Like any powerful technology, quantum computing has a dual nature.
Yeah.
We need to think about the ethical implications. Like, how do we ensure it's used responsibly?
Yeah. How do we make sure it doesn't fall into the wrong hands?
Exactly.
That's a lot of responsibility.
It is, but it's a conversation we need to be having.
Yeah, as we push the boundaries of what's possible.
Exactly. Open discussion is crucial as we enter this new frontier.
Definitely.
But the potential benefits are too significant to ignore.
Yeah, you're right. So where does Microsoft's Majorana-1 fit into this?
Right. So while many are attempting to build quantum computers,
right,
Majorana-1 is special because it leverages these unique properties of Majorana particles.
Oh?
It's a completely different approach.
And it has the potential to be far more robust and scalable.
Okay, I'm really starting to see why this is a big deal. But if this is so promising, why haven't we seen these topological quantum computers yet?
Well, it comes down to the difficulty of creating and controlling these particles.
Okay.
It requires really specific conditions and materials.
Yeah.
And even then, success isn't guaranteed.
Wow.
It's like trying to build a house of cards in a hurricane.
They're pushing the limits of what's possible.
Exactly. So they've been at it for years. And Majorana-1 is a significant step forward.
Yeah.
It's still early.
Okay.
There are still many hurdles. But the potential payoff is enormous.
It really is.
It's a testament to human ingenuity.
Yeah.
Our pursuit to understand the universe.
It's amazing we've come this far.
It is.
From grocery shopping to the quantum realm.
Yeah.
It's been a journey, but I have a feeling we're just getting started.
Oh, absolutely.
Yeah.
We've only scratched the surface of what Majorana particles can do. Okay, like what?
Remember how we talked about braiding them?
Vaguely. How does that work again?
So imagine choreographing a dance where two Majorana particles exchange places.
Okay.
That's essentially what braiding is.
Okay.
And the outcome of that dance actually carries out a computation.
So just by moving these particles around,
yeah,
we can perform calculations.
Pretty much.
That sounds like magic.
It's as close to magic as we get in physics.
Yeah.
And the beauty is this type of computation is inherently fault tolerant.
Okay.
Because remember, the information is encoded in the topology.
Yeah, like weaving a tapestry.
Exactly.
Even if a few threads come loose, the overall pattern is still there.
Exactly. And that's what makes Majorana-based qubits so revolutionary.
Okay.
They're the path towards truly reliable, scalable quantum computers.
Now I'm getting it. So if we can achieve that level of scalability, what should we be looking out for?
So one of the biggest challenges is scaling up from the handful of particles.
Right. To the thousands or millions needed.
Right. For a truly powerful computer.
Exactly.
So how do we get there?
It'll require advances in material science, nanofabrication, and, of course, our understanding of quantum physics.
That sounds like a lot.
It's a long road ahead.
Yeah.
But the potential rewards are world-changing.
So this quantum computing race is heating up.
It is.
What do you think will determine the winner?
It's not just about building a working quantum computer.
Okay.
It's about building one that is powerful and practical.
Right. So it can solve.
Exactly.
Yeah.
A machine that can tackle real-world problems.
Your problem.
In a way that's accessible and beneficial.
I can't wait to see what the future holds.
Me too. It's a really exciting time to be alive.
Yeah, this has been incredible.
It has.
This deep dive into Majorana topoconductors. I'm still trying to wrap my head around it all.
It is a lot.
But this technology really has the potential to change the world. This deep dive has been quite a journey.
We started with the grocery list.
Yeah.
And now we're talking about technology that could change the world.
It's amazing how the universe is full of these unexpected connections just waiting for us to, uncover them.
Yeah, who knew that a grocery list had anything to do with quantum computers?
Right, it's mind-blowing.
So we were just talking about scaling up this technology.
Yeah.
What needs to happen for Majorana-based quantum computers to, actually happen?
So right now we're working with a pretty small number of Majorana particles.
Okay.
To build a useful quantum computer, we need to scale that up, significantly.
Okay.
Thousands or even millions of these particles all interacting in a controlled way.
Wow. That's
really difficult.
That's a huge challenge.
So what are the biggest hurdles?
Well, it's multifaceted.
Yeah.
We need to improve how we create and control these particles with incredible precision. This means pushing the boundaries of materials science.
Okay.
Developing new techniques for nanofabrication.
Yeah. So it's not just about refining our theoretical understanding of how these systems behave.
Building bigger chips.
Exactly.
Yeah.
It's about developing new materials
that
can host these particles reliably. Designing intricate architectures to control their interactions.
Wow.
And even developing algorithms that can use their properties for computation.
It's a massive undertaking.
It is, but the rewards are huge.
It makes you wonder what the world will look like when we have quantum computers.
It really does.
What are you most excited about?
I'm excited about the potential to change fields like medicine, materials science, and AI.
Like what specifically?
Imagine designing personalized medicine based on your genes.
Wow.
Or creating self-healing materials.
That's crazy.
Or AI that can solve problems that normal computers can't even touch.
That sounds like a huge leap forward.
It really does, like the invention of the internet or electricity.
It really does.
And remember, this is just one approach to quantum computing.
Oh, right.
There are others out there,
each
with their own strengths and weaknesses.
So it's a race to see who unlocks the quantum world first.
It is. And the winner will be the one who makes it practical and accessible.
Yeah, it can't just be powerful. It has to actually be useful.
Exactly.
Well, this has been an incredible race to follow.
It has.
And I can't wait to see who wins.
Me neither. It's a really exciting time to be alive.
It really is. And it just shows that even the most complex scientific ideas can have a huge impact on the world.
They really can.
And who knows what other discoveries are out there.
Exactly. There's so much more to explore.
Well, that's it for our deep dive into Majorana topoconductors.
It was a good one.
We hope you learned something new.
Yeah.
You've sent over a whole stack of research papers, notes, even some excited forum posts.
Really?
All buzzing about a potential connection between quantum physics and the Riemann hypothesis. That sounds like something out of a science fiction movie.
It does, doesn't it? But what's so fascinating about these sources is that they lay out a surprisingly compelling case. Remember, the Riemann hypothesis is this notoriously difficult problem that's been puzzling mathematicians for over a century and a half.
Yeah.
It's all about trying to understand the location of these special points called zeros of a function called the Riemann zeta function. Imagine you're searching for buried treasure on a map. But instead of X marks the spot, you have this intricate mathematical function guiding you.
I'm picturing a treasure map, but instead of pirates and islands, we've got complex numbers and mathematical functions.
Exactly.
So these zeros, these buried treasures, what's the big deal about finding them?
Well, it turns out the location of these zeros is deeply connected to the distribution of prime numbers. Think of prime numbers as the building blocks of all other numbers.
Right.
And understanding how they're distributed is essential for all sorts of things like cryptography, the science of keeping our online information secure.
So if we could crack the Riemann hypothesis, we'd not only solve a major mathematical puzzle, we might even make our online world more secure.
Potentially, yeah.
That's pretty high stakes.
It is high stakes.
But you mentioned quantum physics. How do they even start to connect those two worlds?
That's where things get really interesting. These sources are exploring something called the Hilbert-Polya conjecture. It's like a bridge between the abstract world of mathematics and the real physical world of quantum mechanics.
I'm intrigued. Tell me more about this bridge.
This conjecture suggests that there might be a real physical quantum system out there whose energy levels, the very essence of how it behaves, correspond exactly to the location of those mysterious zeros on our mathematical treasure map. It's like those zeros aren't just abstract mathematical points. No. They're a reflection of something fundamental about the physical universe.
Wow, that's a pretty mind-blowing idea.
Yeah.
So instead of just trying to solve equations on paper,
right,
these researchers are trying to build a physical system that embodies the Riemann hypothesis.
That's exactly it.
That's thinking outside the box.
It really is. And to make things even more interesting, the system they're building relies on these incredibly weird particles called Majorana-Fermions. These are particles that are their own antiparticles, meaning they have this incredible stability.
Okay, back up a second. Majorana-Fermions.
Yeah.
Antiparticles. Feeling a little lost.
Think of it like this. Imagine a mirror that not only reflects your image, but also creates a perfect copy of you, but made of antimatter. That copy is your antiparticle.
Okay.
Now, most particles, when they meet their antiparticle, they annihilate each other. Poof, gone.
Right.
But Majorana-Fermions are so unique that they are their own antiparticle. It's like they're looking into that mirror and seeing themselves perfectly stable and unfazed.
So these Majorana-Fermions are like the ultimate introverts of the particle world.
Yeah.
Perfectly content to be their own company.
Exactly, exactly.
But how do they fit to this whole Riemann hypothesis puzzle?
Well, just like the non-trivial zeros on the critical line show a kind of stability, Majorana-Fermions are remarkably stable. Researchers believe this stability might be the key to building a quantum system that can mimic the behavior of the Riemann zeta function.
All right, so we've got this super abstract mathematical problem. This really strange type of particle. And this ambitious conjecture trying to link them all together. How do they actually start to build this quantum system?
Well,
what are the building blocks?
The heart of their system is a special mathematical object called a Hamiltonian.
Okay.
You can think of it like the instruction manual for the quantum system. It dictates how the system evolves over time, what its energy levels are, and how it behaves overall.
So they're crafting a specific Hamiltonian that's somehow designed to capture the essence of the Riemann zeta function.
Exactly.
That sounds incredibly complex.
It is.
What does it even look like?
They start with these Majorana-Fermion operators, kind of like the basic ingredients in their recipe. Then they combine these operators in a specific way to create the Hamiltonian and infinite dimensional.
Whoa, infinite dimensional.
Yeah.
My brain is already starting to hurt.
Think of it like this. Remember that treasure map analogy?
Yeah.
Well, imagine that map stretches out infinitely in all directions. That's what we mean by infinite dimensional. It's a system that, in theory, has an unlimited number of possibilities.
Okay, I'm starting to get a sense of the scale of what they're trying to do here.
Yeah.
But how do prime numbers fit into all of this? We started with a math problem about prime numbers. But now we're talking about infinite dimensional quantum systems and weird particles.
The prime number information gets baked right into the system through a special matrix denoted as AC. This matrix describes how different parts of the system interact with each other, and it's constructed using something called the von Mangolt function, a way to encode information about prime numbers directly into the system.
So they're building prime number information right into the fabric of the quantum system, and there's this decay parameter that you mentioned. What does that control?
Imagine you're trying to build a giant network of interconnected nodes. The decay parameter controls how strong the connections between those nodes are. In this case, it dictates how strongly the Majorana-Fermions interact with each other. You can think of it as a knob they can turn to adjust the overall behavior of the system.
So they're carefully crafting this Hamiltonian. Using Majorana-Fermions. Encoding prime number information. And fine-tuning the interactions with this decay parameter. It sounds like a lot of work just to get the system set up.
It is, and they don't stop there.
Oh, really?
They go through a very rigorous process to prove that the Hamiltonian they've constructed is self-adjoint. This is a crucial property in quantum mechanics because it guarantees that the system will have real, measurable energy levels.
I'm starting to see why self-adjointness is important. If we want those energy levels to match up with the zeros of the zeta function, they need to be actual numbers. Not some weird abstract mathematical concepts. But I'm still a bit fuzzy on how they actually make that connection.
Yeah.
How they show that the energy levels of this crazy quantum system are the same as the zeros of the Riemann Zeta function.
That's where things get even more interesting. And it's where these researchers dive deep into some seriously advanced math.
Oh, boy.
They explore a variety of techniques to make this connection.
Yeah.
The Resolvent Trace, the heat kernel, and the Spectral determinant. Each one is like a different tool they can use to analyze the system and look for those telltale signs of the Riemann hypothesis.
All right, I'm ready to dive deeper. Let's start with the Resolvent Trace. What is that and how does it help?
The Resolvent Trace is like a fingerprint of the system's energy levels. It captures information about how the system responds to different energy inputs.
So it's like they're poking the system with different amounts of energy and seeing how it reacts. And they're hoping to see a pattern in those reactions that matches the pattern of the Riemann zeros.
Exactly. And what they find when they analyze this Resolvent Trace is quite remarkable. They formally show that it's connected to the derivative of the Riemann zeta function. It's like they're seeing a faint outline of the Riemann hypothesis emerging from the quantum system.
That's incredible. But you said they formally show this connection. Does that mean there are still some gaps in the proof?
Well, there are still some challenges in rigorously proving this link. They encounter potentially divergent sums, and they need to be very careful with something called analytic continuation, a way to extend the domain of a complex function. It's like they're trying to navigate a mathematical minefield, making sure every step they take is logically sound.
So they're walking a tightrope,
Yeah.
trying to push the math as far as they can, while still making sure they don't fall into any logical traps. I'm starting to get a sense of how challenging this problem really is.
It is incredibly challenging, but that's what makes it so exciting. And they don't stop with the Resolvent Trace. They also use this sophisticated mathematical technique. It's called heat kernel regularization to define the spectral determinant of H.
Okay, now you're really testing my math vocabulary. What is a spectral determinant, and why do they need to regularize it? It sounds like they're performing surgery on this mathematical object.
Think of the spectral determinant as a way to summarize all the system's energy levels in a single compact function. It's like condensing all the information about the system's energy into one neat package. But when you're dealing with an infinite dimensional system, things can get messy. You can end up with infinities popping up all over the place, which makes it very difficult to work with.
So regularization is like a way to tame those infinities.
Exactly.
To make the math more manageable.
Exactly. Heat kernel regularization is a way to smooth out those rough edges to make the spectral determinant well-behaved and finite. It's like they're sanding down the edges of a piece of wood to make it perfectly smooth.
I'm starting to see the need for all this fancy math. They're dealing with a very delicate
and
potentially explosive object, and they need the right tools to handle it carefully.
Precisely. And what they find when they apply this heat kernel regularization is that the spectral determinant of H, or at least they aim to show that it's directly proportional to the Riemann zeta function. That's a huge deal. Because it means that the zeros of the zeta function, those buried treasures we talked about, would correspond perfectly to the energy levels of H.
If they can rigorously prove that, it would be a monumental breakthrough.
It would be amazing.
But you keep saying aim to show. It sounds like there are still some hurdles to clear.
There are. One of the biggest challenges they face is dealing with the infinite dimensional nature of the problem. Remember that infinitely stretching treasure map?
Yes.
Well, it turns out it's very difficult to work with an infinitely large system directly. So they do what any clever mathematician would do. They break the problem down into smaller, more manageable pieces.
That makes sense. It's like trying to understand a giant complex machine by first studying its individual parts. So how do they break down this infinite dimensional system?
They construct finite dimensional approximations, denoted as Hn, to the full Hamiltonian H. Think of these as smaller, simplified versions of the full system.
So instead of trying to tackle the entire infinite treasure map at once, they're focusing on smaller, finite regions.
Exactly. And here's where things get really exciting. even in these finite approximations,
Oh, really?
they start to see hints of the Riemann hypothesis emerging.
Okay, I'm on the edge of my seat. What kind of hints are they seeing?
They find that the eigenvalues of these finite dimensional versions of H, which are essentially the energy levels of these smaller systems, exhibit a specific statistical pattern known as GUE statistics.
GE statistics. Now, that's a new one. What are GE statistics?
Why are they important?
GUE stands for Gaussian Unitary Ensemble. It's a way to describe the statistical properties of a certain class of random matrices. And it turns out that the zeros of the Riemann zeta function are known to exhibit GUE statistics.
Hold on. So both the energy levels of their finite approximations and the zeros of the Riemann zeta function show the same statistical pattern. That's more than just a coincidence, right?
It's a very strong sign that they're on the right track. It suggests that their Hamiltonian, even in these simplified finite dimensional forms, is capturing something fundamental about the structure of the Riemann zeta function.
Oh, wow.
And remember that Resolvent Trace we talked about?
Oh, yeah.
Well, when they analyze it for these finite approximations, they find an expression that looks strikingly similar to the logarithmic derivative of the zeta function.
Oh, wow.
Plus an extra term.
So they're getting tantalizingly close to connecting the quantum system directly to the Riemann zeta function. But what about that extra term?
Yeah.
Is that a problem?
It's a bit of a mystery. They claim that this extra term is an entire function, which means it's well-behaved and doesn't have any nasty singularities, but they don't fully explore its properties or explain where it comes from. That's one of the areas where more work is needed.
It's like they found a hidden passageway that leads almost to the treasure.
Yeah.
But there's this mysterious locked door blocking the way.
Right.
Still, it's incredibly exciting to see how far they've come.
It really is. They've built a solid quantum system.
Yeah.
Shown some very promising connections to the Riemann zeta function. And they're starting to see evidence of the Riemann hypothesis emerging from their work. But there's still a big hurdle to overcome. They need to show that these findings from the finite approximations hold true for the full infinite dimensional system. That's where the real challenge lies.
It sounds like they've laid out the blueprints, gathered the materials, even built a scale model of this incredible mathematical bridge.
Yeah, that's a good way to put it.
Now comes the hard part, constructing the full-scale version.
Exactly. And that's where we'll pick up in the next part of our deep dive. We'll explore the techniques they're using to handle that tricky transition to the infinite dimensional system, the concept of convergence, and what it would mean for the world of mathematics if they actually succeed in proving this century-old hypothesis. Stay tuned.
Sounds good.
Yeah.
All right, we're back and ready to tackle the next stage of this mathematical climb.
Yeah.
We left off with these researchers building a fascinating quantum system using those strange Majorana-Fermions.
Right.
And showing some pretty compelling connections to the Riemann zeta function.
Okay.
At least in those smaller, finite dimensional versions of their system. But the real test, the summit of this mathematical mountain, is proving it all holds true.
Yes.
For the full, infinitely vast system.
Right. That sounds daunting. It is, but it's also what makes this whole endeavor so captivating. Remember, the core challenge is to rigorously prove that the energy levels of their quantum system line up perfectly with the zeros of the Riemann zeta function, with no stragglers on either side.
Right.
It's like making sure every guest at a giant party has a unique seat at an infinitely long table with no empty chairs and no one left standing.
Okay, that's a pretty vivid analogy.
Yeah.
But how do they even begin to tackle that kind of problem?
Well,
it's like trying to organize a party for an infinite number of guests.
One key step is to focus on the spectral density, denoted as NT. Think of it like a population density map for the energy levels of the quantum system. It tells you how densely packed the energy levels are in different regions.
So it's like a way to visualize how crowded the energy landscape of the system is.
Exactly. And what they need to show is that this NT matches perfectly with a formula that describes the expected distribution of Riemann zeros, called the Riemann von Mangold formula.
So if their NT matches the Riemann von Mangold formula, then the energy levels match the zeros, and boom, they've proven the Riemann hypothesis.
Exactly.
It's like solving two jigsaw puzzles and finding that they fit together perfectly.
That's the dream. But remember, we're dealing with an infinite dimensional system, which makes things much trickier.
Right.
To handle this, they use those finite approximations, those smaller, more manageable versions of the system, and then they have to show that as these approximations grow larger, they converge to the full infinite system.
Okay, so convergence is like a guarantee that those smaller puzzles, as they grow larger and more detailed, will eventually reveal the same picture as the infinitely large puzzle.
Precisely. But proving convergence in this case is no easy feat. They have to show that their results from the finite approximations, those tantalizing hints of the Riemann hypothesis we talked about earlier, aren't just flukes, that they actually reflect the true nature of the infinite system.
Right, so proving convergence is key, but even with those smaller systems, how do they connect that prime number information encoded in that matrix A to the distribution of energy levels? That spectral density and T. It still feels like there's a missing link.
There are actually several paths they're exploring to bridge this gap, each with its own strengths and challenges. They call these the Toeplitz operator approach, the Mellin transform approach, and the Selberg type trace formula approach. It's like they're trying to climb this mathematical mountain, and they've identified 3 different routes to the summit.
I love that analogy. So each path offers a different set of tools and strategies.
Exactly.
For reaching the top. Let's explore each one, starting with the Toeplitz operator approach. What's the idea behind that?
The Toeplitz operator approach focuses on the special structure of that matrix A. It turns out that A is almost a special type of matrix called a Toeplitz matrix. Toeplitz matrices have this nice property that they can be analyzed using a symbol function denoted as A. The symbol function is like a simplified representation of the matrix, capturing a lot of information about its properties.
So it's like they're trying to find a simpler, more compact way to describe this complex matrix. Hoping it will reveal some hidden connections to the Riemann zeta function.
The idea is that if they can analyze the symbol function, they might be able to relate the distribution of eigenvalues of A, which are connected to the energy levels of the quantum system, to the distribution of Riemann zeros.
But you said A is almost a Toeplitz matrix.
Does that almost create problems?
It does. It complicates things. Because many of the nice theorems about Toeplitz matrices don't apply perfectly in this case. To make this approach work, they need to rigorously justify that AC is close enough to a true Toeplitz matrix for the relevant theorems to apply. It's like they're trying to use a key that almost fit the lock, but needs a bit of tweaking to turn smoothly.
So it's a delicate balancing act.
It is.
Trying to exploit the properties of Toeplitz matrices while still being mindful of the subtle ways in which AC deviates from the ideal. What about the second path? The Mellin transform approach. What's that all about?
The Mellin transform is a powerful mathematical tool that's often used in number theory to analyze functions that involve prime numbers. In this approach, the key is to apply the Mellin transform to the trace of the heat kernel of H. Remember that heat kernel regularization we talked about?
Yes.
Well, the heat kernel is another way to capture information about the distribution of energy levels in the system.
So it's like the resolvent trace, another fingerprint of the system's energy landscape.
Exactly. And by applying the Mellin transform to the trace of this heat kernel, they're essentially transforming the problem into a different mathematical domain. One where they might be able to see connections to the Riemann zeta function more clearly.
It's like they're using a special lens to examine the system from a different angle. Hoping to spot some hidden patterns that were previously obscured.
Yeah, that's a great way to put it. And this approach has the potential to be very powerful. If they can carefully analyze the Mellin transform of the heat kernel trace and connect it back to the Riemann zeta function, it would be a major step towards proving the hypothesis.
I'm sensing a pattern here. Both the Toeplitz operator approach and the Mellin transform approach
involve using sophisticated mathematical tools to analyze the system from different perspectives, hoping to find those hidden connections to the Riemann zeta function. What about the third path? The Selberg type trace formula. What makes that one special?
The Selberg-type trace formula, if they can derive it for their specific Hamiltonian, would provide the most direct and elegant link between the quantum system and the Riemann zeta function. It's a powerful formula that relates the geometry of a system to its spectral properties.
Geometry. Now you've really lost me. We started with a math problem, then we went to quantum physics, and now we're talking about geometry. Yeah. How does geometry even fit into all of this?
Remember that matrix ACK encodes prime number information?
Right.
Right?
Yeah.
Well, you can think of the distribution of prime numbers as having a kind of geometry to it. It's not a traditional geometric shape, like a circle or a square, but it has its own unique structure and patterns.
Okay, so it's like a different kind of geometry.
Yeah.
A geometry of numbers.
Yes.
Where prime numbers are the building blocks.
Exactly. And the Selberg-type trace formula, if they can derive it for their Hamiltonian, would connect the geometry of this prime number landscape to the energy levels of the quantum system. Those eigenvalues we talked about.
Right.
It's like finding a secret map that shows how the layout of prime numbers influences the behavior of this quantum system.
That sounds incredibly profound.
It is. It is.
But you said if they can derive it.
Yeah.
Does that mean it's particularly challenging?
It's definitely the most ambitious of the three approaches. Deriving a Selberg-type trace formula for this specific Hamiltonian would be a major mathematical accomplishment.
Wow.
But if they can pull it off, it would be incredibly elegant and convincing.
So they've got these three different paths to the summit, each with its own set of challenges and rewards. But in all of these approaches, there's this underlying challenge of proving that there's no extra baggage in the spectrum. What exactly does that mean?
It means they need to make absolutely sure that there are no energy levels in the quantum system that don't correspond to a zero of the Riemann zeta function, and vice versa.
Right.
Every zero needs a matching energy level, and every energy level needs a matching zero. No leftovers, no mismatches.
It's like making sure every guest at that infinite party has a designated seat.
Exactly.
And there are no empty seats left over.
Yeah.
How do they plan to guarantee such a perfect match?
That's where they bring in another powerful mathematical tool, the spectral measure. The spectral measure is like a way to describe how the energy levels of the quantum system are distributed, how much weight each energy level carries.
So it's like a histogram that shows the distribution of energy levels.
Exactly. They aim to show that the spectral measure of their approximate system converges to a measure whose density perfectly matches the expected distribution of Riemann zeros described by that Riemann von Mangold formula we keep coming back to.
So they're using the spectral measure to make sure that the energy levels are distributed in just the right way to match the Riemann zeros with no unexpected bumps or gaps in the distribution. But how do they handle the transition from those finite approximations to the full infinite system? That seems like a tricky step where things could easily go wrong.
That's where things get really subtle and challenging. They need to show that as the finite approximations grow larger, the spectral measure converges smoothly and doesn't introduce any extra energy levels that weren't there before. It's like making sure that as you add more guests to that infinite party, they all find their designated seats without disrupting the overall seating arrangement.
All right, so no gate crashers at this mathematical party.
Exactly.
But how do they actually prove that the spectral measure converges in such a well-behaved way?
That's where those GUE statistics we talked about earlier come into play. Remember how both the energy levels of the finite approximations and the zeros of the Riemann zeta function exhibit GUE statistics?
Right. That was a pretty compelling clue that they're on the right track.
Well, it turns out that GUE statistics suggest a kind of repulsion between the energy levels. It's like each energy level has a little force field around it, pushing other levels away. This repulsion prevents the energy levels from clustering too closely together and helps ensure that they spread out in just the right way to match the Riemann zeros.
So it's like quantum physics is enforcing a kind of social distancing from the energy levels.
Exactly.
Making sure everyone has enough space and no one gets left out.
That's a great analogy.
It is. And it's a testament to the depth and rigor of their approach. Yeah. They're using statistical properties of random matrices and quantum systems to address one of the most subtle and challenging aspects of the proof. Yeah. Making sure there's no extra baggage, no mismatched energy levels in their quantum system.
So they've built this incredibly complex quantum system.
It is.
Encoded prime number information into its very fabric.
Right.
Found multiple ways to connect it to the Riemann Zeta function. Yeah. And developed techniques to ensure there's no extra baggage in the energy level distribution. That's seriously impressive.
It is. It is.
But are we at the summit yet?
Not quite.
Have they proven the Riemann hypothesis?
They've laid out a very detailed and ambitious plan, a roadmap for proving the Riemann hypothesis. They've shown some very promising results.
And made significant progress. But the most challenging part, actually rigorously deriving that spectral density, using one of those three approaches, and proving that it converges to the expected distribution of Riemann zeros for the full infinite dimensional system, is still ahead of them.
So it's not quite there yet.
They're like explorers who have charted the course, gathered supplies, and reached base camp. But the final ascent to the summit, the most treacherous part of the journey, is still to come.
It sounds like they've done the groundwork. They've got the right equipment and a good map. Yeah. But the final push to the summit is going to require all their skill, ingenuity, and a bit of luck. What are the biggest challenges they face in this final stage of the climb? What are the obstacles that could stand between them and the summit?
Each of those three paths, the tuplets operator approach, the Mellon transform approach, and the Selberg-type trace formula approach presents its own unique set of obstacles. For the tuplets operator approach, they need to rigorously justify applying a powerful theorem called the Sego limit theorem to their almost tuplets matrix Ike. And they need to connect that symbol function, ANAC, which captures information about the distribution of prime numbers, to the formula that describes the distribution of Riemann zeros.
It sounds like a delicate maneuver.
It is, it is.
Like trying to thread a needle while riding a unicycle on a tightrope?
Exactly.
One wrong move, and the whole thing could unravel.
It requires a deep understanding of both the theory of Toeplitz operators and the intricacies of the Riemann Zeta function. And for the Mellon transform approach, they face the tricky task of proving that the Mellon transform of the heat kernel trace exists, that they can manipulate it in the right way, and then invert it to recover that crucial spectral density. And of course, they need to show that this spectral density is related to the Riemann Zeta function in a very precise way, using the prime number information encoded in ACAC.
It's like they're trying to decipher a secret message written in the language of prime numbers, using the tools of quantum mechanics and advanced mathematical transforms.
That's a great analogy. It highlights the interdisciplinary nature of this research, the way it brings together ideas from different fields to tackle a problem that has stumped mathematicians for over a century.
And for that final, most audacious path, the Selberg-type trace formula, what are the main hurdles there?
That one's a real beast. Deriving a Selberg-type trace formula for their specific Hamiltonian would be a feat of mathematical ingenuity. They need to carefully analyze the trace of a function of h, potentially expanding it as a power series and using the unique properties of Majorana operators. Then they need to connect this expression to the well-established trace formulas from analytic number theory, ultimately demonstrating that the prime encoding in ACK leads to a trace that reflects the distribution of Riemann zeros. It's like building a bridge across a vast chasm using materials that have never been combined before.
It sounds like they're pushing the very boundaries of mathematics. Forging new connections between seemingly disparate fields. It's like they're creating a whole new language to describe the hidden patterns of prime numbers.
Exactly. And that's what makes this research so exciting. It's not just about proving a theorem. It's about expanding our understanding of the deep connections between different areas of mathematics and physics. It's about finding new ways to think about some of the most fundamental questions in science. It's about the thrill of exploration. And the potential to make a truly groundbreaking contribution to human knowledge.
This deep dive has taken us on quite a journey already.
It has.
We've gone from a seemingly abstract math problem to the world of quantum physics, explored fascinating concepts like Majorana-Fermions and spectral measures, and witnessed the creation of a whole new framework for understanding the mysteries of prime numbers. But the biggest question remains, will they succeed?
Yeah, that's the question.
Will they reach the summit of this mathematical Everest and finally plant their flag on the Riemann hypothesis?
That's the question that keeps mathematicians and physicists up at night.
Yeah.
And it's a question we'll explore in the final part of our deep dive. We'll delve into the potential implications of their work, the broader significance of this audacious quest, and what it all means for our understanding of the universe. Stay tuned.
I can't wait.
Yeah, it's going to be good.
We're back for the final stretch of our Riemann hypothesis deep dive. We've been on quite a journey, from abstract number theory to the bizarre world of quantum particles, all in pursuit of this elusive mathematical treasure. We've seen the groundwork these researchers have laid, the intricate system they've built, and multiple paths they're exploring to reach the summit of this mathematical Mount Everest. But now the big question looms. What if they actually pull it off? What if they manage to prove the Riemann hypothesis using this wild quantum physics approach? What happens then?
Well, it would be a seismic event in the world of mathematics. Imagine a problem that has stumped the brightest minds for over 160 years, a problem so challenging that it's become almost legendary. Now imagine a group of researchers using tools and concepts that seem completely unrelated, cracking that problem wide open. It would be a testament to the power of human ingenuity, the unexpected connections that underlie seemingly disparate fields of study, and the sheer thrill of venturing into the unknown.
I'm getting goosebumps just thinking about it. But beyond the sheer intellectual achievement, would there be any practical implications? I mean, this all started with a pretty abstract math problem about the distribution of prime numbers. How does that translate into something that impacts the real world?
That's the amazing thing about math. It often seems abstract and disconnected from everyday life, but it's actually the language that describes the underlying structure of our universe. And the Riemann hypothesis, even though it seems esoteric, has profound implications for many areas of science and technology, especially cryptography.
Cryptography, that's the science of keeping our online information secure, right?
Exactly. The security of our online transactions, our communications, even our national security relies heavily on encryption algorithms that use prime numbers. The better we understand the distribution of prime numbers, the stronger our encryption methods can be.
So, proving the Riemann hypothesis could literally make the online world a safer place. That's a pretty compelling reason to care about a seemingly obscure math problem. What else? Are there any other potential impacts beyond cryptography?
It's hard to predict all the ripple effects of such a fundamental breakthrough, but history has shown us time and time again that advances in pure mathematics often lead to unexpected technological innovations down the road. This deeper understanding of prime numbers could lead to more efficient algorithms for data analysis, faster and more powerful computers, even breakthroughs in fields like physics and engineering that rely on complex mathematical models.
It's like opening a door to a whole new universe of possibilities. It's amazing to think that a solution to this one problem could have such far-reaching consequences. But let's be realistic for a moment. We've talked about how incredibly challenging this problem is, the intricate steps involved in their proof, and the potential pitfalls along the way. What are the chances they'll actually succeed?
The challenges are undeniable. They're pushing the boundaries of several fields of mathematics, working at the very edge of what's currently known and understood. But here's the thing. Even if they don't fully succeed in proving the Riemann hypothesis, their work is already incredibly valuable.
How so? If they don't reach the summit, what's the point of the climb?
Think of it like this. Imagine a group of explorers setting out to discover a new continent. They might not find the fabled city of gold, but along the way, they map the terrain, discover new resources, and pave the way for future explorers. That's what these researchers are doing. They're developing new mathematical tools, exploring unexpected connections between different fields, and creating a whole new framework for thinking about the Riemann hypothesis. Even if they don't plant the flag on the summit, they're leaving behind a rich legacy of knowledge and inspiration for others to build upon.
So, they're pioneers, charting a course through uncharted mathematical territory. And whether or not they reach their ultimate destination, their journey will have a lasting impact on the world of mathematics.
Exactly. And that's one of the most beautiful things about science and mathematics. It's not always about finding the answers. It's about the pursuit of knowledge, the willingness to ask bold questions, and the courage to explore the unknown. It's about that spark of curiosity that drives us to understand the world around us, even if the answers are elusive and the path is fraught with challenges.
This has been an incredible deep dive, and I think I speak for both of us when I say that we've learned a ton along the way. We've explored a problem that has puzzled mathematicians for generations, seen how quantum physics might offer a surprising solution, and considered the profound implications of such a breakthrough. But what's the final takeaway for our listener? What should they be thinking about after this deep dive?
I think the most important takeaway is this. The pursuit of knowledge is an adventure, and sometimes the most unexpected paths lead to the most profound discoveries. The Riemann hypothesis has challenged mathematicians for over a century, and these researchers are approaching it from a completely fresh perspective, using tools and concepts that no one had considered before. Whether they succeed or not, their work is a testament to the power of human ingenuity, the interconnectedness of seemingly disparate fields of study, and the enduring allure of unsolved mysteries.
It's a reminder that we're constantly pushing the boundaries of what we know and understand, and that the most exciting discoveries often lie at the intersection of seemingly unrelated fields. So stay curious, keep exploring, and never be afraid to challenge the limits of what's possible. Who knows, maybe you'll be the one to crack the next great mathematical mystery. Thanks for joining us on this deep dive.